Hey, Calc 1 fans. We're continuing the lecture from yesterday. And yesterday, we computed our first derivatives. And remember what the derivative of a function is? We represent the derivative with this symbol, f prime of x. And the derivative of a function is an expression that gives the slope of the line tangent to the graph of the original function for any value of x. And we're going to do another example very much like the one that we did yesterday, just for the sake of reinforcement. Here we're working with the function f of x equals the square root of 2x plus 1. And our instructions are, compute the slope of the tangent at the following points on the graph of f of x. Well, when they say compute the slope or compute the slope of the tangent, immediately we think derivative. And we're exactly right to do that. So the first thing for us to do is to compute the derivative f prime. The derivative f prime of x will give us the slope of the line tangent at any point on the graph of f of x. Right now, we only have one tool in our tool bag for computing the derivative, and here it is. We call this the definition of derivative. It's the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. Okay, on your mark, get set, go. The first thing we have to do is compute f evaluated at x plus delta x. And notice, here's our model of f of x up here. This is f evaluated at x. This is f evaluated at x plus delta x. So x plus delta x plays the role down here that x plays up here in our definition or our model of f of x. So every place that we see an x up here in our model of f of x, we're going to put x plus delta x down here. Well, we see an x up here, so down here we're going to put x plus delta x. Every place we see an x up here in our model, we put x plus delta x down here. So this is f evaluated at x plus delta x. Next, we subtract f of x. Square root of 2x minus 1, or 2x plus 1 rather. And then the whole thing is over delta x. Remember yesterday when we computed the derivative by the definition and we plugged in delta x right off the bat? We got 0 over 0. The same thing is going to happen this time. And in fact, the same thing usually happens when we compute the derivative using the definition and we plug in 0 for delta x right off the bat. If we plug in 0 for delta x, we're going to get a 0 here and a 0 here. So we'll have 2x plus 1 square root minus 2x plus 1 square root. We're going to get 0 in the numerator. And plugging in 0 for delta x, we're going to get 0 in the denominator. So if we plug in delta x right off the bat, we get 0 over 0. That's no good. But it does tell us something. It tells us that we expect to be able to cancel out a common factor in top and bottom. And once we cancel out that common factor, then we can go back in and plug in 0 for delta x. And this is the factor that we want to cancel from top and bottom. The only problem is the factor of delta x in the numerator is hidden because of these radicals. We've got to get rid of the radicals before we can find that factor of square root of x in the numerator and cancel. So, how do we get rid of the square roots? How do we get rid of the radicals? And if you're saying to yourself, I know, multiply by the radical conjugate, top and bottom, you're absolutely right. We're going to multiply top and bottom by the radical conjugate, and that will eliminate all of the square roots in the numerator. Okay, there's our original expression. And to get the radical conjugate, we take these two square roots and change the sign in between. So we'll have square root of 2x plus delta x plus 1 plus square root of 2x plus 1. You see, we changed the sign in between. And now we have to multiply the denominator by the same thing. And when we multiply a radical pair by its conjugate, do you remember what we get? We get the first thing squared minus the second thing squared. So here's the first thing squared. Here's the second thing squared. Now in the bottom, I did something interesting, something curiously interesting. Notice in the top, I multiplied all of this out. And when I did, I got the first thing squared minus the second thing squared. And on the bottom, I didn't multiply anything out. I didn't distribute this delta x to these two terms. And the reason is, I'm pretty sure that this is the factor that I want to cancel from the denominator. And because of that, I want to make sure that I keep this factor exposed. So I didn't distribute the delta x to these two terms. I just kept this factor and this factor separate. Now, forgive me, I don't feel like bending over, so I will continue up here, up top. So let's see, I get this thing squared, so that's 2 quantity x plus delta x plus 1 minus 2x plus 1. So essentially this thing minus this thing all over the denominator, which I am not going to multiply out. And I guess the last thing that I have to do is distribute this 2 inside the parentheses. So I'll get 2x plus 2 delta x and I'll distribute the negative sign inside this set of parentheses. So I'll get negative 2x minus 1 and let's see what happens. I have a plus 2x here and a minus 2x here. They zap each other. I have a 1 here and a negative 1 here. They zap each other. The only term in the numerator that survives has a factor of delta x. All of the terms that did not have a factor of delta x get zapped. They cancel each other out. And remember, things worked exactly that way in the example we did yesterday. So when we're computing a derivative using the definition, we expect that all of the terms in the numerator that have a factor of delta x will survive, and all of the terms in the numerator that don't have a factor of delta x will be annihilated. Well, let's pick up the pieces here. I have a delta x on top and a delta x on the bottom. Square root of 2x plus delta x quantity plus 1. You know what? I'm not going to have enough room to write this, so I will just continue on the line below. So I have 2 delta x on top, and I have delta x on the bottom, square root of 2 quantity x plus delta x plus 1, plus square root of 2x plus 1, and here's that factor of delta x in the numerator that wasn't revealed because of the radicals that were present. So we have a factor of delta x in the numerator, a factor of delta x in the denominator, and we cancel those out. Now, let me ask you something. In this expression, we canceled out the delta x's. And the delta x's, the factors of delta x, were what were causing division by 0. So in this step, we got rid of the troublemakers. So, what do you think that we should do in this step now that we've gotten rid of the troublemakers? Plug in, right? The question is, what do I plug in and where do I plug it in? What is it that's approaching 0? Is it x that's approaching 0? It's delta x, isn't it? Delta x is approaching 0. So we will plug in 0. What will we plug in 0 for? If delta x is approaching 0, then we'll plug in 0 wherever we see a delta x. Remember, these x's are different variables. Delta x and x, they're completely different variables, just like x and y are completely different variables. So delta x is approaching 0. So we'll plug in 0 for delta x. So we have 2 factors of square root of 2x plus 1. So that will give us 2 square root of 2x plus 1. And just to simplify a little bit further, we'll cancel out the 2's here. Now that we have our answer, maybe we should take a step back and think about what it was we were trying to compute in the first place. Oh, we've taken 10 or 12 steps at least. And in all that time, it's likely that we forgot what it was that we were trying to do. What were we trying to do, and what is this? Remember, we were computing the derivative, and this is it. Now, don't make the mistake that I always make. I got an answer here, and my tendency is always to say, I did it, I'm done, I got the answer. You know, I do that all the time because I don't stop and check what it was I was trying to do to begin with. Now, I know I was trying to compute the derivative, but is that what the directions told me? Let's see, didn't the directions tell me that I wanted to compute the slope of the line tangent to the graph of f of x at 3 different points, where x was equal to 0, where x was equal to 4, where x was equal to 12? Yeah, I almost forgot about that. But this is not my final answer. This is something that I had to do in order to get my final answers. So, let me see if I can reconstruct what it was that we wanted to do in the first place. Part A, I was supposed to find the slope of the tangent at this point. X equals 0, f of x equals 1. And remember, the slope of the tangent is given by the derivative. The derivative is a function of x. So how do you think the derivative is going to tell me what the slope is at this point 0, 1? How will the derivative, which is a function of x, tell me what the slope is at this point 0, 1, where 0 is the x value? If you're thinking that I should take the x value and plug it into the derivative, you're absolutely right. That's exactly what I need to do. So I take the derivative f prime of x and I plug in 0 for x. So I'll get 1 over 2 times 0 plus 1. So at the point 0, 1, the slope of the tangent is 1. Now, part B, we were supposed to find the slope of the tangent at the point x, f of x is equal to, what, 4, 3? I think that's what it was. Yep. And so the slope is going to equal f prime evaluated at the x coordinate. So f prime evaluated at 4. And to get that, we look at the derivative, and wherever we see an x, we plug in 4. So at the point x, f of x equal to 4, 3, the slope is given by the derivative, which equals 1/3. And last but not least, I think I also said we wanted the slope of the tangent at the point x, f of x equal to 12, 5. Was that right? I don't know where I get all these weird numbers. Must have been all those drugs I did when I was a kid. I'm kidding. Yeah, 12, 5. Okay. At the point x, f of x equals 12, 5. The slope is equal to the derivative. And since the derivative is a function of x, we plug the x value into the derivative to get the slope. Okay, let's see. 1 over square root of 25, I think that's something that even I can do. So, at the point x, f of x equal to 12, 5, the slope is 1/5. And I think I will cut this video short and immediately begin another, just because we're going to handle the topic of derivative from a completely different perspective. in the next video. I will give you some homework from the text to accompany this video. And as soon as I stop taping this video and post it, I'll go back to making another video, which I will also release today, that has to do with derivatives, but we'll look at it from a completely different perspective.